Hello, folks. This is Cargo. For everyone's here, thanks so much for coming. This is something that I've been wanting to do for a while. I actually did a test run of it last night. But essentially, what we're going to be doing is I'm going to be doing a quick, like, 1 hour crash course on Arduino and embedded systems. This is kind of like my field of expertise in what I'm studying. So, figure I might try to spread some of that knowledge around. See if anyone is interested. um, but yeah, essentially what we're going to be doing today, it kind of like as a vehicle in order to kind of get more familiar with the Arduino platform, microcontrollers in general, embedded systems in general, is we're going to try to create a night light circuit. You guys are probably familiar with how a night light works. It's basically when you plug it into the wall, right? And when a room goes dark, when you're getting ready to sleep or something like that, or yeah, something like that, the light will automatically turn on. And then similarly, when you turn on your regular lights in your room, the night light will automatically turn off. So how does it do that? That's something that we can achieve using an embedded system. We don't have to use a microcontroller necessarily, but we do need some sort of circuit. And in this case, just to kind of familiarize all of you guys with this Arduino platform, I figured we would try to implement the logic on the code side as well. So without further ado, let me get this pulled up. Yes. Okay. So, hopefully everybody can see this. Oh, you know what? I probably want to move my camera down to this bottom left corner because I think right now it is covering some important things. Okay. Cool. That should be good. Okay. So what you see in front of you right now is the completed nightlight circuit. And so I will point out three kind of important parts here, and we'll go into detail on what their function is here as well. So here first is the Arduino I was talking about. This is, oh shoot, sorry. I forgot to start recording. I was gonna record this. Um, Okay, I'm gonna start recording, and then let's pretend like I just transitioned to this. Okay, hey guys. So this is our completed nightlight circuit. There are three main components here that I want you guys to take a look at. The first thing is our Arduino right here at the bottom. This is kind of the brains of our operation. This is where we're going to be putting in all of our logic and actually saying like, okay, like if we take this input and look at the value of the input, what do we do with that? Like depending on that. All an embedded system really is a black box. It's similar to a function. You go way back into like your math class, where you learned about functions. You put your x input in, you take your y output out, right? And the function does something to it. You don't necessarily need to know what that something is in order to use the function. Similarly, if I hand you a nightlight, like you don't need to understand like internally how the nightlight works in order to plug it into your wall and make use of it. And so we're using our Arduino here in order to kind of abstract away that like logic component of this project. Um, cool. So that's the Arduino down. I'll come back to it and describe exactly what some of these sections on the Arduino are. But let's talk about next our photoresistor right up here. So that's the guy that I just highlighted in blue now. It's got the little squiggly line on the top, right? So our photoresistor is a type of resistor. When you think of the word resist, think that it blocks the flow of current. It blocks the flow of electricity. Because the current is just a measurement of I suppose the speed at which electricity flows, although that's a little bit of a misnomer. But yeah, essentially, what a photoresistor does is it acts similarly to a resistor, except that it doesn't have a static resistance, which means that and so here's where the photo part of the name comes in, right? With a photoresistor, depending on how much light is present in your environment, the resistance of the photoresistor will change. So if there's less light, I believe the resistance will increase, and if there's more light, the resistance will decrease. I believe that is uh, the correct combination there. But anyways, if it wasn't correct, you could just flip flop your wires and be fine. But yeah, so that's what the function of our photoresistor in this circuit. We're going to look at, I suppose, how much electricity gets through the photoresistor, for lack of a better, I guess, layman's term. We're gonna look at that, and depending on how much light gets through, we're going to either turn on or turn off our LED. This is our LED right here. This is going to act like our light bulb that we would have put in our nightlight. Actually, there's probably some nightlights that use LEDs too. But besides the point. So we're going to pretend like this LED is our nightlight, and we're going to turn on and off. So that's the only function, is basically of the LED, is it'll either light up or it'll not light up. So yeah, think I've explained both of those things pretty well. Again, if you guys have any questions on, if you have questions on getting set up, there's this command, exclamation point setup, that tells you how to kind of get to a blank page like the one I have open right here. If you have any questions about anything that I just went over with regards to the Arduino, photoresistor, the LED, then yeah, definitely let me know in chat or something like that, and I'm happy to answer that. Happy to kind of make it a little bit more, help you guys understand exactly what's going on here, because that's going to be kind of crucial, obviously, if you want to make this yourself one day, or make something similar one day. But yeah, if there's no questions, the next thing that I want to talk about is specifically on the Arduino, the pin selection that we have. So check out here, check out our digital PWM section here. You see how it's labeled digital PWM? I'm hovering my mouse over it. So what this section is it's basically a selection of pins that can output either a high signal or a low signal. If you guys are familiar with more electrical terms, it's a high voltage or a low voltage. If you're more familiar with software, it's going to be like a binary 1 or a binary 0. So it's kind of a either you get it or you don't situation, right? And so you can see here that we've made one connection from our Arduino, from our Arduino's digital pins to our LED, and that goes through a resistor. So let's explain what's going on here. Essentially, as we said before, we can either turn the LED on or keep it off. There's a little bit of nuance there that I'll explain once we finish building our nightlight circuit. There is a way that you can actually change the brightness of the LED technically. But I'll come back to that though. But yeah, essentially, just think of it as an on-off kind of switch that the Arduino controls. Now, okay, on the other hand, these digital pins can also be used as an input. So right here, we're outputting some voltage to the LED, right? Which is what makes it turn on. But we can also take in some signal. So say if we had a button, for example with a keyboard or something like that. Look, I've got my keyboard right here. Every time I click one of these buttons, there's a microcontroller inside my keyboard that keeps track of, oh, which button did he just press, and it's able to see okay, which of these, so with the keyboard, it's kind of a bunch of rows and a bunch of columns of wires. So it creates kind of like an array, a kind of a grid system, if you will. And so how the keyboard can see which key I press is it sees, okay, which row is selected and which column is selected, and it can bring it right down to that single key. So we can do kind of a similar thing here, right? So if we have a digital input, one that just goes high or low, like a light switch or a button or a keyboard switch or something like that. Whenever we press it or release it, like it'll change the value that's going into one of these pins. So we can use our digital pins for input or output. Now here on the other side of the board, you'll see the section called analog in. If you're familiar with the terms digital and analog, then you'll know that analog is a much more continuous scale than digital, right? Because digital, it's kind of a binary option, right? It's either yes or no. It's either high or low. With analog, there's the high and the low, and then there's all the values in between as well. And so, you know, it's not practical to be able to convert those values, like, you know, directly into code, because when you're coding something, you have to use specific values, right? And unfortunately, you know, converting a continuous scale to a discrete scale does remove some of the resolution. So, you know, say if I had one signal that was 2.0000 volts, and then I had one that was 2.00001 volts, or something like that. If I'm using an completely analog, you know, measurement tool, something like an analog multimeter or something like that, in order to determine the voltage difference between these two signals, then I'll be able to tell, like, oh yeah, it's this like minuscule amount. But on something like an Arduino, these analog pins, like between the actual pins themselves and the processor that's on board, it goes through something called an ADC, an analog to digital converter. Essentially, what this is doing is saying, like, okay, if my value for if the value of this voltage that's coming into this pin is between, you know, 0 and, you know, some value, then set it to value 0. If it's between this value and the next value, set it to value 1, and so on. Let me turn this music down quickly. I didn't think it was going to get that loud. Anyways. Oops, not too much. Cool. I didn't think it was going to get that loud. Yeah, so this ADC, analog to digital converter. So the Arduino, the one that's on board the Arduino, will convert these voltages 0 to 5 volts into 0 to 1023. So you get 1024 possible values between 0 and 5 volts. Now, obviously, in real life, there is an infinite amount of voltage values between 0 and 5 volts, right? Like, you can go decimals. You can go 4.5. You can go 4.0005. And that might not be accurately represented by the digital scale, but it's the best we can do in this situation. So 0 to 1023, we have 1024 possible values. That'll be important for later when we start coding stuff. Our last section here on the Arduino is the power section. We have a right here we have a 5-volt connection and a ground connection going here. There's also a few other connections like V in, ground, 3.3 volt. You can read about those if you need to use them in some project that you're doing. But for now, let's just focus on the 5-volt and the ground. So yeah, that's everything that I wanted to explain here on our built circuit. So now let's go to our new circuit and start rebuilding the circuit. Okay, so first thing we need, obviously, is we need the Arduino and we need the breadboard. If I'm going to assume that people watching this are probably not familiar with how a breadboard works, so I will give a quick crash course. Essentially, And maybe it'll be easier if I rotate this to explain. Okay, so you can see here on either side of the board, I have these positive and negative columns, correct? And see how when I hover over them, I get the whole column lit up. So all of these pins are connected. So if I draw a wire from, let's say, my 5-volt pin down here, and I connect it to the end of this rail, so now actually all of these pins are connected to this 5-volt connection. Similarly, if I take my ground and I do the same thing, then now all of my negative pins in this column, are connected to my ground on my Arduino. And so we can also, in Tinkercad, we can also change the colors of these wires up here. So if I click the wire and then I come up here, I can change it to black for the negative and red for the positive. But I'm going to delete those for now. I just wanted to rotate this breadboard into kind of the correct orientation for 1 second just to explain the columns and the rows. So you've seen those two sides now. So now let's look at the kind of the main center area. This is where we're going to be doing all our actual wiring. So here you can see that we have these A, B, C, D, E, and then F, G, H, I, J columns, and we have rows 1 through 30. It's important to note two things. So first of all, the rows are connected in the center area, not the columns. So when I say 1, like row 1, like that entire row 1 is connected. But it is broken in the middle. So columns A, B, C, D, and E of row 1 are connected, but they are separate from columns F, G, H, I, and J of row 1. And similarly, row 1 is not connected to row 2 or row 3 or any of the other rows. So you can see that with the green highlighting here, but essentially row 1 on the left side of this board has these 5 pins that it's connected to. And that will come in handy when we need to connect multiple wires potentially to the same terminal on our photoresistor, for example. So with that, I'm going to put this back in the original orientation. It'll just make our build process here a little bit simpler. So let's go ahead and draw our 5-volt and our ground signal wires here. So I'm going to draw this around. I'm going to try to make it neat. If it isn't neat, I apologize. And then we'll get our ground. And we'll need to change the color of this one, of course. Cool. And then we'll make that one black. Cool. Okay, so now we are delivering power from our Arduino to this power rail. What this will allow us to do is it'll allow us to connect power from the power rail to any of our components on the board here, rather than having to pull it all the way from the bottom of the Arduino here. So yeah, that's that. Okay, so now remember that we have a photoresistor and an LED that we had to connect. I'm going to start with the easier one. The easier one to connect right here is going to be the LED. I think it's a lot more straightforward. So I'm going to put an LED here. Let's make it a green LED. Why not? Okay, so there's an important thing to note here. So an LED stands for light emitting diode. I might have already said that, but just to make it clear. And so what that means is that it is a diode. That's the D in LED, which means that current will only flow through it one way, or it's only supposed to flow through it in one direction. And so it is important to note which leg is the cathode and which leg is the anode, meaning which leg do we connect to ground and which leg do we connect to our power source. And so you can see here in the illustration here that there's one leg that's like a little bit bent. So imagine if you straightened that leg out. It would be longer, right? The kind of like the bent leg would be longer than the straight leg. So the bent leg, the one that would be longer, is going to be the one that we connect to our power source. That is going to be our anode. You can see here when I hover over it, it says anode. When I hover over the shorter one, it says cathode. And so what we're going to do here is we're going to take one of our digital pins. I'm just choosing D3 at random. You can choose whatever you'd like. I would stray away from choosing 1 or 0, just because those are used for communication protocols. But 3 is a completely valid choice. You can choose anything from 2 to 13 without too much issue. So I'm going to draw a wire from 3 up to my anode like this, and notice that I don't have to connect it to the same pin right here. I can connect it down here on column F instead, and have it connect to that long leg directly. And we'll make this wire green. And with our other leg, we're going to take that and connect it just back to our ground. So that will be just a regular, just a black wire, because that's also a ground connection. Okay, so you might think we're done here, but there's a slight there's something I have to go over here with regards to how we're directly connecting power to our LED. So you guys are probably familiar with light bulbs burning out, right? The filament breaks and then the light bulb doesn't light up anymore. Something similar can happen to most electronic components, where it like lets out a little bit of like magic smoke, and then suddenly it's not usable anymore. It's broken, and that's usually because too much power went through some component on the system. Our LEDs are an example of one place where that can happen. In order to prevent too much current from going through our LED, we need to put a resistor in series, so kind of along the path of the circuit, in order to prevent that from occurring. So how we're going to do that, let's move this end of the wire down to this side of the board, and let's grab ourselves a resistor. Remember, just make sure you grab just a regular resistor. And you can put it right here. And now that you've put that down, this will prevent too much current from passing through the resistor, and in turn, it'll prevent too much current from passing through the LED. Think about a pipe, right? If there is a really small section of a pipe, then no matter how big the rest of the sections are, you're gonna get a bottleneck at this small section of the pipe, and that's going to limit the speed of the water that can go through any other part. It's similar with like traffic flow, right? If your 3-lane highway suddenly becomes just a 1-lane bridge, then the speed of everybody, on the side of the, before the bridge is going to be limited by the speed of the people crossing the bridge. So it's the same way, right? If I put in a resistor, then the speed of the current, or I guess the speed, the flow of electricity is limited by the resistor, and thus that same speed of electricity will also flow through the LED. So that's the purpose of that resistor there, and that's actually our whole LED circuit. That's all we had to hook up. Okay, so now comes a slightly harder part. We're gonna get our photoresistor. So that's just the word photo next to the word resistor. You can see here, it's this little squiggly guy. We're gonna get that, and let's just put it on our board somewhere. Cool. Okay, so we'll also need a resistor for this part, but let's just do our regular hookups here first. So we're gonna hook up, let's hook up our ground to one leg, okay, and let's hook up our power to the other leg. Okay, so what's wrong here? Well, for starters, we don't have a resistor in place, so if the, I know it's a photoresistor, but there's still a possibility, well, sorry, I'm explaining that wrong. Let's start over. Okay, so the real thing that's wrong here, more than anything else, is that we have no way to measure how much current is passing through our photoresistor. That's what we wanted to measure, right? Because we said that depending on how much light is shining on this photoresistor, the resistance will increase or decrease. And resistance has an inverse relationship with with current given, you know, a static voltage. And so if we increase our resistance, then less current is able to pass through. If we decrease our resistance, more current is able to pass through. And so we need some way to measure, like, okay, how much current is actually passing through though? And the way we're gonna do that is we're going to actually take another wire on this ground leg right here. So we'll take this out, and we're gonna go connect it to one of our analog pins. So why are we connecting this to our analog pin? I'm gonna connect it to pin A0 if you're following along. And let's make this wire orange. Okay, so why are we connecting this here? The reason we're connecting this here is because we need to measure exactly how much current is going through, and the way that we're going to do that is we're basically going to compare. There will be something called a voltage drop over this photoresistor, and that will basically basically a way for us to determine, like, okay, how how much resistance is this currently producing in our circuit. And so what we can do is we can compare. Think of like water pressure. If you have that bottleneck in your pipe somewhere, right? And that bottleneck would be the photoresistor in this case. Imagine you can change the size of the section of the pipe. So what we can measure then is we can come out to the other side of that bottleneck in the pipe, and we can measure, like, okay, like how much water pressure is there. So this red wire has a lot of water pressure, right? But then this black wire has no water pressure. So somewhere in the middle here, we need to determine, like, okay, like how much is this preventing that pressure, that current flow from going through, right? So that's one thing. So we're essentially gonna measure a voltage here on this orange wire. The other thing is, right now we have our ground wire, our negative terminal wire, connected directly to our A0 pin. In this situation, no matter how high the pressure is through here and like how much current is passing through the photoresistor, we've kind of short-circuited our A0 pin directly to ground. So it's just always going to read 0. So how we're going to alleviate this is we're going to put in another resistor, also here on this ground pin. And this is going to be called a pull-down resistor. So this resistor kind of does two things. So in the case that there is actually current passing through our photoresistor, this will make sure that the ground doesn't short circuit to our wire here, because there's this resistor in the middle that's preventing that flow of current, or I guess the lack of flow of current, if you will. The other thing is that the other purpose that this resistor serves is, sorry, let me collect my thoughts. What did I want to say? Yeah, so I talked about how this resistor serves this purpose of preventing this ground wire from directly short-circuiting to my A0, and so therefore, now think about the situation where the photoresistor doesn't have any current flowing through it. Well, now even though this resistor is here, I still end up being able to connect my ground wire here to my A0 through the resistor, because there's no current coming from the other side, and so it'll read that 0. If we didn't have the ground wire at all, like imagine we didn't have either of those, then what would happen is if we didn't have any current flowing through the photoresistor, our orange wire would actually be stuck in something called a floating state. Essentially, it's like we don't know how high or low the voltage is because we don't have any reference. We don't have any reference to compare it to. That's why we need our ground here. Our ground serves as a reference voltage for us to compare whatever's coming through the photoresistor to. So yeah, with that, we actually have a complete circuit here. This is all of the wiring we needed to do for the circuit. So now we can continue on to our actual code. So with Tinkercad, if you go over to this code button right here, then you can open code. It gives you an option either to code in blocks, or you can code, directly in text, or you can code in blocks and see the output in text. I'm gonna start with the blocks and text, and then maybe we can go over to just text. I think this will be easier to visualize for you guys. So let's toss all of these blocks away. They make kind of a funny sound, I'm gonna be honest. But okay, essentially what's happening here, and I don't think I have any way of pulling this out too much more. Like this code window won't come out. That's fine. No worries. Okay, so you guys can still see, oh, you cannot see the circuit. My camera's covering it, kind of. Let me bring this back a little bit. We'll try to... Okay, I think this should be okay. Nice. Okay, cool. So my camera isn't covering that anymore. Sweet. Okay, so what we're gonna do here is think about the logic. Think about what exactly we wanted to achieve here, right? So we're saying that, okay, we're gonna get a value. Remember, so our photoresistor is connected to one of our analog inputs. We said that our analog inputs are gonna be, it's going to give us a value anywhere from 0 to 1023, right? So we need to somehow make a determination of, okay, if the value from the photoresistor goes past a certain value, let's say like 50%. So 512 would be kind of in that middle of 0 to 1023. So let's say if our light intensity value is less than 512, then let's turn our nightlight on. So, which means that like the lights in the room are dim enough to where we should turn on our nightlight. On the other hand, let's say that it goes, that our light intensity value goes over 512. Well, then we want to turn our LED off. We'd just be wasting power, Like there's no reason for it to be on. It's not very bright, right? It's not supposed to be an actual light source, just regularly. It's only supposed to be a light source for the dark. So we don't want it to be on during the daytime or when the lights are on. So how we're going to simulate that is think about kind of the control flow here. So we said, okay, so this is the key word, right? If our value from our photoresistor is less than 512, then turn the light on. Otherwise, or else, that's another key word. So if and else, right? So else, otherwise, if that value is equal to or greater than 512, just making an inclusive range, then we are going to turn our nightlight off. So how do we incorporate this? We're going to take this if then else block from the control scheme, from the control section. Sorry. So what this is going to do is basically if the condition that we put into this little hexagon hole is matched, if it's correct, then we're going to go into this first section, this first open section here. Otherwise, we're going to go into the second open section right here. Okay, so now what are we testing? What is our condition, right? So this is where we're going to need, first we're going to need our input. So we're reading a value from the analog pin A0, right? We're reading our photoresistor, which is connected to analog pin A0. So we take this, and we can't just put this directly in, right? We need to compare it to some other value. So we're going to go over to our math section, where we have this, look at this pointy block right here. This is also a hexagon-shaped block. We need this one. So we're gonna toss this in here. But what do we want to compare? we said we wanted to compare the value from the photoresistor to 512. And we want to check if that value from the analog pin is less than 512. So we'll put this into the left side, and we'll leave the less than, right? And here we're gonna put, on the other side, we're just gonna put 512, just a static value, if you will. Okay, so if that's true, then we need to do some output. Remember, all I said that embedded systems was you give it an input, or you give it multiple inputs, it's a black box, it gives you out an output, or it gives you out some multiple outputs. So we're gonna go to our output section, and we've connected our LED. Just a quick note here. There's this block that says built-in LED. We're not using the built-in LED. We've connected our own LED here. So we're gonna take this the second block here that says set pin whatever to high, or set it to low. So we're gonna take this. We need one for both sections actually. So what we're gonna do here is we're gonna set pin 3. Remember, we connected our LED to digital pin 3. So set pin 3 to high. So if the brightness of the lights in the room are not high enough, then we want to turn on our night light. Otherwise, else, we want to actually set it to low. So we want to turn off the night light in that situation. So this is actually the entire control scheme right here. And so you'll see on our C code side, we have this function called void loop. This is something that's going to continuously occur. Like, it's never going to stop. It'll keep checking this condition in our if statement. It'll keep checking, like, okay, is the value we're reading from our analog pin A0, is it less than 512? And if it is, then we're going to do something called a digital write, which is just writing, a value either high or low to a digital pin. So we're going to write to pin 3, and we're going to set it to high. Otherwise, so if this condition is not true, then we want to digital write pin 3 to low. So essentially, we're either going to turn the LED on, or we're going to turn the LED off. And yeah, that's pretty much all that's happening in the code here. So let's actually start our simulation and see what happens. So I'm gonna go ahead and make this a little bit bigger here, just so that you guys can see what's happening. Okay, so right now, do you see how our LED turned on? Right now, that's because our brightness, whenever we start our simulation again, is just reset to 0. So here you can see we can change the brightness on this photoresistor with this kind of sliding dial that we're given. So right now you can see we're kind of on the dark side, but if we slide over to the brighter side, eventually, kind of around our halfway point, our LED is going to turn off. And then if we slide back to the darker side, our LED will turn back on. So that's that 50% I was talking about. Kind of like that halfway in between value, 512. So we could change that value if we wanted to, but this is just kind of like for demonstration purposes. So yeah, this is our entire nightlight, and this was our code right here. So just to recap what we did, we read our analog pin, which is connected to our photoresistor, and we checked if it was less than 512, kind of that median value for the analog pins, what you can read from them. And so if that was true, then we turned on our night. We set the LED pin to high. Otherwise, we set the LED pin to low. So if the value we read from the analog pin was greater than or equal to 512, then we would set pin 3 to low. So yeah, that's pretty much it, actually. So that is the entire workshop that I wanted to do here. I know that, I guess I didn't really even go for the full hour. If anybody in chat has any questions or wants to see me try to connect something else into this mix, I can certainly can certainly do that. But otherwise, thank you guys so much for coming out to this workshop. This is something that I did for Christopher Yee's Discord server, actually, just last night, and they all really enjoyed it. So I figured I might do a rerun essentially on my own channel, and see if we can get anybody interested in some embedded system stuff. So yeah, with that, that is all I had for today. So if you guys don't have any questions, again, if you do have questions later on, definitely don't hesitate to reach out. You can whisper me on Twitch. I might not see it immediately, but if you send me a message on like Discord or something like that, my Discord server is linked in my about somewhere, or you can message me on just anything really. I'm happy to help with any issues you guys might be having, or any like project ideas or something that you guys are thinking about. But yeah, other than that, thank you so much for coming. And just before we head out, let's find somebody to raid. Oh, I haven't rated Fura in a very long time. All right. Well, Verb, I know what we're doing today. Oh my gosh, this search is so awful. Yeah, Far is watching cooking videos. Interesting. Okay, you guys should enjoy this then. I'll hand you off. Again, guys, thank you so much for coming to the workshop. I'm hoping that this VOD will be useful for people looking at it in the future. I'm gonna also publish this to YouTube. Maybe I'll cut it down a little bit and stuff like that. But yeah, other than that, yeah, thanks for coming. I don't know how many times I've said that now, but yeah, I mean, it means a lot. So yeah, thanks for coming. And I will see you guys on Monday at 10 p.m. EST for I don't know what I'm doing yet. So we'll find out there. All right, peace, guys.